पांडे सर नमस्कार।
Yes, sir. Yeah, namaskar, sir.
Hmm.
Good afternoon. How are you?
बस फाइन सर।
Okay.
है ना, participants are joining sir.
Oh, thank you. Sorry for the delay. I was in class.
नहीं, we already announced in the last lecture we will start at 12 o'clock.
Okay, okay. Thank you, thank you.
And that's not an issue. So now now time is 12 and participants are joining. Just
Okay,
wait
so
for 1-2 minutes and then we will start. Sir.
okay. So I'm going to share the slide. Okay.
Yes, sure. Sir.
फोन कर बढ़ जाए स्क्रीन का मायने
Take care of the mouse.
Ranjit sir, is it visible?
Visible. Visible, sir.
Okay. Now, should I start? Ranjit sir?
Just yes, Indu ma'am.
Hello.
What?
Yes, sir. Good afternoon, Chandan
Please.
sir.
Good afternoon, ma'am.
I welcome you in the second session of third day of this ATAL FDP on design thinking. And I welcome all the participants again. And this is pleasure to me to introduce Dr. Chandan sir with the participants. And I would like to start your introduction with this line that sir have 80 publications in SCI journals, and that is a very big thing. So, Dr. Chandan Pandey is Associate Professor at Department of Mechanical Engineering, IIT.
Ma'am, not associate. I am assistant professor.
My mistake, sir. Sir is Assistant Professor at Department of Mechanical Engineering at IIT Jodhpur. Sir did his BTech from GCT Noida, MTech and PhD from IIT Roorkee. Dr. Pandey awarded twice for Best Paper Awards and twice in top 2% scientist of the world in the world. Besides this, he awarded for Excellence Awards in Mechanical Engineering, and he edited 2 books also. His research interest includes welding, heat treatment, mechanical behavior of material processing, and nuclear grade material. Sir, we are very thankful to you for accepting our invitation for being expert in this session. And I welcome you again, and I request you to share your wisdom with the participants.
Thank you. Yeah, is it visible in full screen mode?
Yes, sir, it's visible.
Yes.
Okay, thank you. Now, my topic was your challenges in your design of dissimilar alloy joining. Now, first thing about your dissimilar alloy joining, why we are going for the dissimilar alloy joining. So, I want to explain the things with an example. Suppose if you talk about the power plant material that I am working in that field, so I want to relate with topic with that power plant material. So why we are going for dissimilar joining in power plant or any industry? So first thing, if you talk about that power plant material, so generally 40% of the world electricity that is produced from coal-fired power plant, and generally about 80 countries they are related or they are working on coal-fired power plants. Now problem is that with your coal-fired power plant, that is about the emission of greenhouse gases, means especially about the carbon dioxide. Now, due to that emission of greenhouse gases, we face so many problems. So now we are working on that, how we can minimize the emission of CO2 in power plant or coal-fired power plant system. So generally, that report is related to the efficiency. Means by improving the efficiency of the power plant, we can minimize the problem related with the emission of greenhouse gases. Now, efficiency of any plant depends upon the operating temperature and pressure of that working fluid. And by increasing the operating temperature and pressure, we can increase the efficiency of the power plant, and ultimately we can minimize or we can reduce the fuel consumption, and ultimately we can reduce the emission of that greenhouse gases. Now, on the basis of working or operating temperature and pressure, there are four different type of the power plant that we use. That is your subcritical, supercritical, and ultra supercritical and advanced ultra supercritical power plant. Currently, we are working with ultra supercritical power plant, and if we compare with that subcritical power plant, we get an increase in efficiency that is about your 7%. Now, in the future target, that is about to achieve the efficiency about 16 to 17%, means that is possible by using that advanced ultra supercritical power plant. Now, till now it is okay, means we are planning for higher efficiency to minimize the emission of gases, greenhouse gases, and to improve the efficiency of the plant. Now, problem is that to operate such high temperature and pressure, means for if you talk about that advanced ultra supercritical power plant, they operate at temperature about 700 to 750 degrees Celsius. If we talk about the subcritical power plant, that operate in the temperature range of 500 to 540 degrees Celsius. So up to 500, 540, that is okay. But if you talk about the operating temperature in the range of 700 to 760, so it is difficult for a material to sustain such high temperature and pressure. So for that purpose, the advanced material has been developed. The advanced material that is comes in the group of your nickel-based alloy, like in Conal 617, 625, 718. They are designed to operate at high temperature about 700 to 750 degrees Celsius. But problem is that in case of nickel-based super alloy, there are so many allying elements like nickel, cobalt, molybdenum, and other one. So that increases the overall cost of that material. So if you are going to produce the overall power plant system by using that nickel-based alloy, that will be very costly. So ultimately what we do, the component which operate at high temperature, is it audible? Is it audible, sir?
Yes, sir.
Yeah. Sorry. To the component which operate at high temperature, that are generally made of that nickel-based super alloy, and component which operate at lower temperature in the range of 400 or 500 or 600, that are made of different material. So that's why it become necessary to join these two material which are operating at different conditions. So that's why we need that dissimilar joining. So that is about your power plant industry. Similarly, in other industry also, if there are two different part and they are working at different operating condition, one suppose that one part that is working in corrosion environment, one part that is in safe environment. So now for corrosion environment, we need a advanced material. So that cost of that material is very high. So we cannot use that material for the room temperature application also or similar condition. So in that case, again, we need the dissimilar joining of these two material. So ultimately, to improve the design thing and to improve the to reduce the cost, material cost, we need the dissimilar joining of two different grade materials. Now, these are the different material that we use. Now, if we talk about the simple joining of the dissimilar material, so the most commonly used joining material, dissimilar joining, that is about your chromium molybdenum steel that we use in power plant, P91, 92, and arsenic, but that we use in petrochemical industry and other one. Similarly, joining up that P91, 92 with the nickel-based super alloy that we use in nuclear grade power plant, arsenic 2 duplex or martensitic 2 duplex that we use in navy section and other one, copper steel, copper aluminum that we use in aerospace industry. So means in there are so many industry they are using dissimilar joining of two different grade materials. Now the dissimilar material joining has various industrial application, and the dissimilar joining is most frequently used in power plant, chemical and your petrochemical industry. and generally we use to save the novel material and to minimize the cost of that one for that advanced material, and we use different things. Now this is the simple example of your boiler head section where we use two different grade material that are exposed at different temperature. That lower portion that is called your steam header that generally operate at temperature of 600 to 620, that is made of your advanced grade material, that is your P91, and the upper portion that is your made of tube and other one that operate at lower temperature in the range of 450 to 500, that is made of low allying element that is called your P22 steel. So similarly we use in other industry also for dissimilar joining of the material. Now for start, now come to your topic design of that welded joint. Means after getting that dissimilar joint, what parameter, what thing we consider to design a component or to design the welded things. Now weld joint that we design that may be subjected to variety of the load. First thing that comes in the mind to design anything where we are going to use the means application of that one. So means weld joint that subjected to variety of load ranging from their simple tensile load to complex combination of torsion, bending, shearing and other one. Similarly, if you talk about that high temperature material, so that are subjected to residual stresses and high temperature tensile stresses. Means once your power plant operate at high temperature and then it comes to your lower temperature, so due to that you will get some amount of the thermal stresses and their variation. So means there are variety of the application and variety of the load that where it operates. So first thing comes in mind during the well design, that is about the application where we are going to use that one and what type of the loading we are going to apply for that purpose. So now the capability of that weld joint to take up to the given load come from the metallic continuity across the member being joined. Means if you are going to join two member, there should be the homogeneity of that mechanical property throughout the section. So generally the major problem in welded joint, if you are going to join two plate or two material, due to the application of the high heat and due to the variation in case of your dissimilar, due to the application of the high heat and due to the variation in their chemical composition, mechanical property, microstructure, we get face so many problems related to the heterogeneity in mechanical property. And once if there is the heterogeneity, always if we design something, what about the assumption that material should be homogeneous and isotropic. But if we come to that welding section, means welding part, it is not possible due to the application of high heat and other one. We get the formation of thermal means heat affected zone due to that high heat input. We get the variation in mechanical property throughout the weld joint and other one. So it is not possible to get the homogeneous microstructure throughout the product in case of your welding. So that is the important thing that we consider. Now the second thing, if we talk about that a product, a poorly designed weld joint can lead to the failure of that component in three different modes, either by elastic deformation, like your bending, torsion, or your soft or other product engineering system. Second thing, it may fail in plastic deformation mode, means change in dimension during the service condition. And the third one about the fracture of the weld joint into two or more pieces under your external tensile force, shear, compression, and other one. So these are the three common modes that we consider for the failure of a weld joint, and especially it is related with the homogeneity and heterogeneity of the weld product that we get. Now, if you talk about the design of weld joint and their mechanical property, so in that case, the stiffness and the rigidity that are the important parameter that we consider for design a weld component. Now, under such condition, weld metal of high modulus of elasticity and rigidity that is deposited for producing a weld joint besides selecting their suitable load resisting cross section area. Now, with the failure criteria of a weld joint is the plastic deformation. So in that case, weld joint are designed on the basis of the yield strength of the weld metal. That is very common thing. Means if it is subjected to plastic deformation, in that case we consider the yield strength. If it is subjected to static load, in that case we consider that ultimate yield strength of that one. While under fatigue and creep condition, design of a weld joint that is based on your specialized approach, which we will discuss after that one. So now under simplified condition, design of the fatigue load that is based on your endurance limit of that one product. So that is mentioned over here. For different type of the loading condition, we use different type of the criteria to get the final design of the product. Now, if you talk about the factor which affect the performance of the weld joint, means I'm coming to design part. Before that, I'm discussing about the main part which we consider. So now welding procedures used for developing a weld joint, which include the edge preparation, plate preparation, weld joint design, type of the weld, number of pass. So first thing, if you talk about that edge preparation, so generally, if your plate thickness, if you want to join a plate of thickness 5 or 8 mm, so simply you can join that plate without application of the filler metal. There are three different type of the welding. I think you all of you know about that one: homogeneous, heterogeneous, and autogeneous. So generally, in case of your autogeneous, if you are not going to use any filler metal, so that it comes in the group of your autogeneous welding process, and simply we can join the plate just by application of the heat. So up to 8 mm, it is easily we can fabricate a weld joint, but if the thickness is more than 8 mm, so it is not easy to penetrate the heat more than that. So in that case, we prepare the edge. We perform the edge preparation at the end of that plate or side of the plate, and we create different type of the groove geometry, V groove, narrow groove, and other one. So the first thing that we consider, that is about the including the edge preparation of that one, and weld joint design that comes in the group of the type of the geometry that we use for the plate having thickness more than 8 or 10 mm. After that, the next thing that we consider, the type of the weld, means fillet weld, butt weld, or other one. After that, total number of passes required to fill that groove geometry, means up to the autogeneous, that is okay. But in case of your heterogeneous and homogeneous, where plate thickness is more, in that case, we create the groove geometry and we fill that groove geometry by using number of filling passes. The overall number of passes that required to fill that geometry, that we also consider, that is important parameter, because the residual stress and overall performance of that joint, that depends upon the number of passes. That number of passes that related with your heat input, means for each pass we use current, voltage, and travel speed. So on the basis of that, we calculate the heat input, and for each pass we calculate different heat input. So overall, to fill that groove geometry, we calculate the overall heat input that is based on your number of pass. So that is the other important criteria to design the weld component. After that, preheating and post weld heat treatment. Generally, that we perform the preheating for some critical material having martensitic structure, because they create the problem during the solidification and in your region of your heat affected zone, and we get the formation of crack in that region. And we also face the problem related with the hydrogen induced cracking. So to overcome these things, we perform the preheating. And if you talk about the post-weld heat treatment, post-weld means heat treatment that we perform just after welding, and that is not required for all type of the material, especially in case of your austenitic material, we don't need any type of the post-weld heat treatment. But in case of your martensitic steel, once after welding, we get the formation of that fresh martensite, and the fresh martensite offer the higher amount of the strength to your weld joint, but at the same time the martensite offer the poor impact of less, means energy absorbing capacity of that weld product that will be less. So that's why we perform the post weld heat treatment in case of your martensitic steel. After that, the other parameter that we consider, that is about your building process, which process we are going to use. Generally, in case of your aerospace application, we don't prefer to add the additional material. So in that case, we use advanced welding like your activated TIG welding, or we use friction stir welding, where we don't use the filler metal to add or to increase the weight of that one. And if you talk about the power plant, chemical and petrochemical industry, here we use that multi-pass TIG welding process, where the plate thickness or joint thickness that is about more than 10 mm. After that, the next thing that we consider, that welding parameter. In that, we consider especially about your welding current, arc length, and welding speed. That arc length, that is related with your arc voltage. By fluctuating that arc length, we can fluctuate or we can vary that your arc voltage. So these parameters also we consider to design a weld component. And generally, if we talk about that next one, that is about protecting that weld contamination from the atmospheric gases. So in that case, that is the common thing that we use two different type of the things. Either we use inert gases to protect that arc column from the environment gases, or we use some electrode covering that after decomposition that provide the flux and environment gases and inert gases to cover that area, or you can say your arc column. So that things also we consider ki either we are going to use shielding gas or we are going to use electrode covering and other thing. So generally, in case of your gas tungsten or welding, activated TIG and the gas metal or welding, we use inert gas like your helium, neon, argon, and other one. And if we talk about that shielded metal and submerged or welding process, in that case, we use some amount of the electrode covering or flux that provide the proper covering to that arc column and your deposited metal and protect that from the atmospheric gases. So these parameters that we consider to design that weld component. Now, as most of above mentioned step of welding procedure influence the metallurgical property and residual stresses in your weld joint, that is very important, because once you will get the residual stresses in your welded component, that will create the problem throughout the service life of the component. So that we have to also consider. And next thing about the metallurgical change means, once suppose your base metal that have some structure, your martensitic, ferritic or other one, once we are going to apply the heat during the process of the welding, to we get the metallurgical change in that one. And most of the cases we get the dissolution of the precipitate present in that material and other thing. So that is very important parameter, that metallurgical change that we get during the process of the welding, that we also consider during the process of the welding and weld joint design. So this is about the factor affecting the performance of the weld joint and the parameter that we consider during the design of the weld component. Now, after that, next thing, design of weld joint and the loading condition. So design of weld joint for static and dynamic load need different approach, because in case of your static load, it is very clear that direction and magnitude become either constant or changes very slowly that we can neglect. But in case of your dynamic loads such as impact, fatigue, thermal stress and other one, we get the continuous change in loading condition. So in that case, the design criteria for that dynamic one, that will be the different as compared to your static one. And in case of your fatigue loading, both magnitude and direction of load may fluctuate. So under the static loading condition, low rate of loading increases the time available for localized yielding. Means in case of your static loading, once a crack initiate, so that will takes enough time to propagate, because of at the tip of that one we get the plastic deformation. Means 1 minute. Suppose this one is your static loading, and once we get the crack initiation at that point, so there is the plastic deformation at the tip of crack, and that resists the failure of that one. But once in case of your dynamic loading condition, once crack initiated, you will get the sudden fracture of that one, and generally it take place at the degree of your 45 degree, at angle of your 45. So in both the cases, we use different approach to design, and different well parameter we consider for that static one and for your dynamic one. Before start of that one, the next important thing, that is about the welding symbol and type of the welding geometry that we use to get a proper weld joint. Is it clear? And am I audible?
Yes, sir.
Yes, sir, you're audible, sir.
What about the slide and other things are clear?
Yeah, visible. Your slide is also visible, sir.
Okay, no, I am asking about the thing that I am explaining. Is it clear?
Yes. Yes, sir.
Okay. So next thing, that is related with your need of that welding symbol. We use different type of the welding symbol for different things. The first thing means, we are not going to, if you talk about the welding, this is just not about the joining. Sometimes what we do, we also utilize that filler metal to deposit a layer over the surface of your workpiece to enhance the mechanical properties, similar to your material science and heat treatment. If you know about that one, there are process of carburizing, nitriding, cyaniding and other one. In that case, what we do, we add some element like carbon, nitrogen and other one. We diffuse that element in the surface to enhance the mechanical properties, especially about the wear resistance and the hardness of that material. So similarly, in case of your welding, we can utilize that filler metal or filler rod to enhance the mechanical property of that surface. So if you are going to join that, if you are going to deposit a layer over the surface of your workpiece, that comes in called bead on plate, and generally that is represented by the first one, that is your bead on plate, just a deposit layer over the surface of the workpiece to enhance the mechanical property. And especially during the process of that joint design, the first thing that the important thing that we consider about the welding parameter and the weld bead geometry. So generally, if you want to optimize the welding process parameter on the basis of the weld bead geometry, what we do for different parameters, suppose this one is the plate, and for different welding parameter, we deposit a layer over the surface of the workpiece, and after that we cut a cross section of that one, and after grinding, etching and polishing, we check the depth of penetration and bead width. So generally on the basis of that depth to width ratio, we select the optimum welding parameter for that process. So that is about your bead on plate. Second one, that fillet weld, in that case both the plate will not be in same plane, and plug or slot that we use in case of your resistance welding process. After that, the most commonly that we use, that is your butt joint. In your butt joint, there are so many symbols: square, V, bevel, U, J, and other one. So generally, if you talk about the square joint, if you are going to produce a weld joint without any edge preparation, without any creating the group, that comes in the group of your square butt joint, and that we use in case of your laser welding or electron beam welding or autogenous gas tungsten arc welding process. Now it is suitable for the plate thickness up to 8 or 10 mm. If the thickness is more than that, in that case we create the different type of the groove geometry, and on the basis of the groove geometry we use different type of the symbols. Suppose the groove geometry is like this. This one is your first plate and this one is your second plate. So here the geometry, the symbol that we use, that is called your V groove. If we create the geometry in one plate and one plate remain as such, then it is called your bevel. After that we create U, J. After that I will discuss their advantage and disadvantage, why we are going to create that one. Now after the next thing that we consider in your weld joint design, that is the type of the joint which we are going to produce during the process. So in that there are 5 type of the joint we use in your welding: butt joint, lap joint, corner edge joint, and your T joint. Now if you talk about that butt joint, that if both the plate are in horizontal plane and aligned with the maximum deviation of 5 degree, then this is a joint that comes, that is called your butt joint. The maximum deviation that is allowed, that is about your 5 degree. After that, your lap joint, if the overlapping plate means both the plate are not in the same plane, and then it is called your lap joint. Here this is about your lap joint. Corner joint, that is made by melting corner of 2 plates being welded, and therefore plates are approximately perpendicular. Here we can keep angle in the range of 75 to 90 degree. If we talk about that edge joint, that is made by melting of edges of 2 plates to be welded, and therefore the plate are almost at angle of 0 to 5 degree. And T joint, if both the plate are at 90 degree, then we can say that is about your T joint. So these are the common type of the joint that we use in case of your welding process. Now the next thing that about your welding weld joint design that we consider, that is about the welding position, means in which position we are going to perform the welding. So in welding, that is very clear, that is about the transfer of metal. If we draw a simple rough diagram of the welding, suppose this one is the plate, and here there is the filler metal. With the help of filler metal, we deposit a layer over the surface of the workpiece. Now, this is not just about the deposition of the layer. There are number of forces involved during the transfer of the molten metal from that tip to your workpiece surface. Especially we consider 2 type of the force. One is about your gravity force and one is about your surface tension force. Now in case of your welding, generally your gravity force that will act in your downward direction, that act as a detaching force, and it allows the flow of molten metal from your electrode tip to your workpiece surface. If we talk about the surface tension force, that act as a retaining force and retain that liquid metal droplet at the tip of your electrode surface. So generally we get the transfer of the metal from your electrode tip to your workpiece surface when your surface tension force reduces, or you can say when gravity force exceed the surface tension force. So now the welding position play a major role during the transfer of the metal. Means if we talk about that flat welding process, here plate to be welded that are placed on your horizontal plane, and weld bead is also deposited horizontally. This is one of the most commonly used and convenient welding position that we use to get the proper weld joint. In case of your flat position welding, it is easy to transfer the liquid metal droplet from the electrode tip to your workpiece because the gravity force that will act in the downward direction. Now, if you talk about the next one, that is about your horizontal welding process. Here, plate to be welded are placed in vertical plane while weld bead is deposited horizontally as shown in the figure. Now, the technique is completely more difficult than the flat welding, and the welding parameter for horizontal welding should be selected carefully for each manipulation and placement of the weld metal at desired location, because in that case we get large amount of the fluctuation of that droplet, and that's why it is not easy to deposit a layer at the intended point. Now the third one, that is about your vertical welding. The plate to be welded are placed on your vertical plane and weld bead are also deposited vertically. Here in case of your vertical welding, again the problem is that if you are going to position a welding torch or electrode tip over there, so gravity force that will act in your downward direction, it is not easy to deposit a layer over that point, means at the intended point. So that is the problem in case of your vertical. And same problem we also face in case of your overhead welding position also. It is not easy to deposit a layer over the surface of your workpiece in overhead welding position, and also it is not easy to protect that arc generated during the process of the welding in overhead welding position, because that gases flow in outward direction. We cannot use the flux or layer another one in the overhead welding position. So the toughest one, that is your overhead welding position, and it is not easy to deposit a layer over that point. Now after that, the next one that is about your groove application that we consider. For that one, which type of the groove will required, means up to 8 mm thickness, that is okay. By using that autogenous, we can make the joint. But beyond that means thickness is more than that. In that case, we prepare the groove, and generally we prepare U, V, and J type of the groove. So here we prepare two type of the groove. Either we prepare single groove weld or we prepare the double groove weld. Now, if you talk about the single groove means a preparation of the plate to produce detached groove from one side, only resulting in just one face and one root of the weld. While in case of your double groove, a preparation is needed from both the side of the plate. Means here, if you talk about the single V, that is like this. This is the plate. In case of your double V, so here things are very clear. Now, single groove weld is mainly used in case of plate of thickness more than 5 and less than 15. Means less than 5, then it is okay. We can join just by application of the heat. And up to 15 mm, we can use single groove weld. Now, moreover, the bench is not very hard and fast, and it depends upon the penetration capability of welding process. And other thing we also consider that like the distortion that comes during the process of the welding, means plate get distorted due to the application of the heat, and you will get the angular distortion like this. So we also consider that distortion and residual stress that comes in the welded joint. So on the basis of that, we select the single groove weld for the plate, and generally we consider up to thickness of 15 mm. Now the second one, that is about your double groove weld. That double groove is preparation that is used especially under two conditions. First one, if your thickness is more than 15, generally we prefer the thickness more than 25, and desired penetration up to root from one side is not possible. And second thing that we consider, that is about the distortion control. Means in case of your single groove wheel, the major problem that we face during the design, that is about the distortion that comes in the picture. So if the distortion is too much high, in that case we prefer the double groove wheel, and we can compensate. Means during the deposition on one side, suppose we get the distortion like this. During the deposition on second side, again you will get the distortion like this. So you can compensate the distortion that comes in the picture. To for that one, we prefer that double groove wheel. These are the some common type of the groove geometry that we use in case of your butt joint. Here this is the single V, after that triple, double V, and other one. And for each one there is some specific root thickness, root height, and the groove angle. Means they are fixed about that one. Nowadays the most commonly we use, this is the common one that are proposed in SME and the presidential standard, but other that we use, that is about U and J. The why we are going for that J and U type of the groove joint. Actually, in case of your wheel joint, the major comes in case of your V and U, V and bevel. That is about the sharp corner. In case of your V joint, there is the sharp corner at that point. Here, to do that we get higher amount of the stress concentration. You are from the design, so you know very well about the stress concentration. So if there is a stress concentration point, and if you are going to apply the load either static or dynamic or anyone, in that case you will get the maximum amount of stress concentration. As we know that stress concentration factor, that is your 1 plus 2a by v, if we consider the elliptical hole like this. And if we consider the circular one, so that stress concentration factor that comes about 3. So here we get the maximum stress at the stress concentration point. That will be the 3 times of the nominal stress. Means the stress that we apply to maximum stress at that concentration point will be the 3 times of the normal stress that we are going to apply. So due to that, we get the failure of that welded joint. So if we consider these factors, so we provide some amount of the radius over there. Means we remove that sharp corner and we provide some amount of the radius over there to overcome the problem related with your stress concentration. So now the most commonly, it is very clear, the most commonly one that we use, that is about V groove joint, bevel groove joint, after that U and J groove joint. Now, if you talk about that U and J groove geometry, that is more economical in terms of the volume of the metal deposited, because the distortion and the residual stresses that comes in your weld joint, that depends upon the overall heat input and overall deposited metal on the surface of the workpiece. So if somehow we can minimize the deposition of the metal, means overall deposited metal and overall heat input, we can control the problem related with the residual stress and distortion. Okay. So in case of your U and groove geometry, U and J type of the groove geometry, the volume of the weld metal to be deposited, that is less, and that's why it offers less amount of the distortion and residual stress related problem, and besides for higher welding speed. But these groove geometries suffer from difficult in machining. Means it's not easy to create a groove geometry like this. It is difficult to machine that one. So that is the problem associated with your U and J. But the advantage of that one, that will offer of the deposition of the metal, and that's why we get good amount of the mechanical property due to the less amount of the distortion and the residual stress. Now, about your D and bevel groove geometry, that can be easily economically produced in machining or frame cutting. So means it is easy to process, it is easy to manufacture V and groove geometry, V and bevel groove geometry as compared to your U and J groove geometry. But problem is that in V and bevel groove geometry, the overall deposit will be more, and at the same time you will get large amount of the distortion and deflection and the residual stress in that case. So that's why we don't prefer that type of the groove geometry. To mean it is possible, and the cost is not the criteria, In that case, we prefer U and J type of the glue geometry for making a proper weld joint. Now the square glue geometry, they don't need any type of the edge preparation as I discussed, except to make it clear square. But the geometry can be used only up to the thickness of 8 or 10 mm. However, this limit significantly depends upon the penetration capability of that process. Nowadays, we are using advanced process, means activated TIG welding process. In that, in some cases, they achieve the penetration up to 12 or 15. But it is material specific. It is not possible to achieve such penetration for all type of the material by using that activated TIG process. Now, after that, the other thing that we consider that welding and your weld geometry, because overall performance of that weld joint that depends upon one parameter, that is about your weld bead geometry. That is your weld bead geometry. And here there are two things. One is about your depth of penetration, and the second one is about your bead width. So that bead width and depth of penetration are, we can say, the cross-section area of the weld joint that depends upon the current voltage and your travel speed. So generally that very common and detailed things I'm not going to discuss about that one. The depth of penetration that is associated with the current. By increasing the amount of current, we can increase the depth of penetration. But beyond the limit, it will create a problem like melt through another one. Similarly, if you talk about the R that is associated with your bead width, by increasing we can increase the bead width. But beyond the limit, it will show the problem like convectivity and convexity. So that's why again we avoid the too much voltage. There should be optimum level. If you talk about the welding speed, after the welding current, the most important parameter that affect the depth of penetration, that is about your welding speed and travel speed. So again, associated with your depth of penetration. So by optimizing that welding parameter, we can optimize the weld bead geometry, and ultimately we can improve the performance of that weld joint. Now the other thing that we consider, that is about the formation of the heat affected zone, means overall performance of the joint not only depends upon the weld bead, that means weld bead area, that is important one, but the other thing that we consider, that is about the formation of the heat affected zone. Now again, the formation of the heat affected zone, that depends upon the material we are going to weld. For type of the material, they offer different thermal conductivity, and the heat affected zone formation that depends upon the flow of heat of the weld in the region of base metal. So generally that depends upon the thermal conductivity. If the conductivity will be more, in that case we get the wide range of the heat affected zone, and there may be strength of the heat affected zone may be more or less as compared to the weld metal. So again, that contributes a heterogeneity to your weldment and create a problem related to the failure of the weld joint. So that thing also we consider. After that, the formation of some type of the new grains in the region of your heat affected zone due to the recrystallization, and that offer the higher tendency for that growth in corrosive environment, so that again create the problem and ultimately affect the overall performance of the weld joint. So up to here, this is all about the basic things that we consider to make a proper weld joint in case of your weld joint design. Now after that, come to the point of de-single joining. Until now, if you have any doubt or things, you can ask related to that. Is it clear about the basic things of the welding? Do you want to ask anything regarding that? Anyone? Ravi sir?
Hello, sir. So it seems, yes, sir, you are audible.
Is it audible?
Anybody wants to ask anything?
Dr. Indu?
Yes, sir. Sir, I'm asking participants.
Dr. Indu is audible?
Yes, sir, you're audible. I'm requesting participant to ask
Okay.
anything if they have doubt or anything else. I mean, if they.
Okay.
So you're audible. Your PPT is also visible.
Yeah, I know. I'm waiting for the response. No problem.
It seems they are getting everything.
Okay, so should I proceed?
Continue, sir.
Okay. Now, if come to the point, joining up two different grade materials means having different chemical composition, different microstructure, different mechanical property. What type of the problem we face? First thing that was related with the design aspect means what parameter we consider, what type of the group geometry we will select for that one, and what type of the problem related to distortion and residual stresses come during that process. Now, if we specifically if we come to the dissimilar material, joining of the dissimilar material, in that case, what type of the problem we may face, that is very important. So there are a number of parameters that we consider. In that, the first one that is about the selection of the filler metal. Means in case of your autogeneous, there is no need of the filler metal. In case of your homogeneous and heterogeneous, in the composition of the base metal and filler metal are same, that comes in the group of your homogeneous. If the composition are not same, that comes in the group of your heterogeneous. Now, if you talk about this dissimilar joining, so it is not possible to select a filler metal with matching composition of both the planes. You have two plates of different composition, so you select the filler metal having composition similar to either of one plate, depends upon your requirement. But that create the very much problem if the composition, suppose you have two material, one is your steel, mild steel, and one is your austenitic steel. So composition of both one are different, and if you are going to select a filler metal, so it becomes very difficult to select either matching composition with your mild steel or matching composition with your austenitic steel. So now that is the first thing that creates the problem, that is about selection of filler metal, and after making number of tests, after making number of joint, and after complete characterization, metallography and mechanical characterization, we optimize the composition of the filler metal for any type of the process. After that, heterogeneity mechanical property. Heterogeneity in mechanical property, that is very common. That is because of the application of the heat and heating and cooling at high temperature and low temperature. Heterogeneity, and that is very common. But problem is that in case of your dissimilar welding, heterogeneity comes not due to the application of the heat. It comes also due to the application of the filler metal and composition not similar to base metal. And also, if the composition is not same, that filler metal will solidify in different nature as compared to your base and other two base metals. So that create the problem like your heterogeneity in your mechanical property. After that, some soft patches or soft delta ferrite formation. Again, that is material specific. In case of your steel, if there is ferrite and austenite stabilizer, if there is austenite, that will lead the formation of austenite. If there is a ferrite stabilizer like your chromium, molybdenum, and tungsten, that will lead the formation of the delta ferrite. Again, that will create the heterogeneity during the dissimilar joint. After that, the martensitic microstructure, generally, if the either you will get austenitic, perlitic, ferritic, or martensitic. In case of your perlitic, ferritic, and austenitic, there is no problem. But during the dissimilar joint, if you are getting the formation of the martensite in the joint, that will create the problem, because always martensite, that is the structure having higher carbon percentage, and that offer good amount of the strength and hardness, but at the same time it offered the poor amount of the impact of it. So that's why we don't prefer the untempered martensite in the region of your weld metal. So that will again create the problem in joining of dissimilar material. After that, diffusion of element along the interface of your weld and HAJ. Now, the composition of both base metal and filler metal are not same. So during the process of the joining, what happens? The element like iron, nickel, molybdenum, and chromium, they get diffused from the region of metal to base metal, or from the region of your base metal to weld metal, and they form different zones just near to the interface of your weld metal. So again, that create the problem. After that, formation of that unmixed zone formation, that depends again upon the composition of the filler metal. If the composition of your base and filler that is not same, so the filler metal will melt but will not mix properly with the base metal. So due to this portion of filler or unmixed portion of that base metal, that lead the formation of that unmixed zone, and that categorized by the peninsula and island that is called. I will discuss in detail after that. After that, the migration of the element. In migration, especially we consider about the diffusion of the carbon element, because the diffusion of carbon always create the heterogeneity in mechanical property, that because hardness of any material that is steel material that is related with the carbon. So if the carbon percentage will be more, or that hardness of that one will be more. So if the carbon diffuse from one side to other side, so that will lead the formation of the carbon depleted region and carbon enriched region. So again, that is the problem in case of your dissimilar joining. After that, the hydrogen induced cracking. The hydrogen induced cracking that occurs just after welding or after a long period or certain period of the time. The hydrogen induced cracking that is especially related with the diffusible hydrogen content present in the weld metal. During the process of the joining, your arc is at high temperature, and when diffusible hydrogen comes in that well deposited metal, that will move from one portion to other portion and create the vacant point in that region. And due to that, we get the failure of the well joint during the service condition. So that is related with your hydrogen induced cracking. After that, the next one, that cold cracking in multi-stick stainless steel. Again, that is similar to your hydrogen induced. And after that, the most important one, that is about your residual stress, how it comes and how it will play their role during the service life of a dissimilar welded component. Now, from an example, I want to explain. The first thing is very clear, that is about the optimization of the glue geometry. Once after we can start the process, once after the optimization of that weld glue geometry, and I discussed about the different type of the glue geometry, and on the basis of the plate thickness and on the basis of the requirement, we select a optimum glue geometry. After selection of that optimum glue geometry, the next thing in design part, that is related with the selection of the filler metal. If you don't know about the behavior of the metal, in that case, we can perform the number of trials. Means we can select number of filler metal with matching composition of one or two plate, and we can perform the number of weld bead over the surface of your piece. And after making that, after cutting that section, we can measure the weld bead, depth of penetration, and other parameter. We can also measure the mechanical property of the deposited metal, and on the basis of that, we select the optimum filler metal for that one. After selecting glue geometry, filler metal, next thing about the welding process. So that depends upon the application where we are going to use. On the basis of that, we select the process. And generally, the most commonly we use process in industrial area now, that is gas tungsten welding, activated TIG welding. And if you talk about that aerospace application, that is your laser beam welding, electron beam, and your friction stir welding process. Now, if we talk about the heterogeneity, heterogeneity comes from two different regions. One that comes from the filler metal. So in case of filler metal, we all know the composition. In case of your dissimilar, both are different. So due to that, your weld metal solidify in different manner as compared to your base metal. So that heterogeneity comes in the region of your weld metal. Now, the second thing, if we come to the region of your base metal, the part of base metal that is affected by the heat, it is called your heat affected zone. So that depends upon the overall conductivity of that base material. If the conductivity is more like chromium, molybdenum, steel, so in that case we get the wide range of that heat affected zone. In case of your stainless steel, if the conductivity is very poor, in that case we get a very narrow region of your heat affected zone. So generally, a very narrow region, in that case, it will not create the problem during the service condition. But in case of your wide region, you get the continuous change in the microstructure and mechanical property when we move from the fusion boundary to the region of your base metal through the heat affected zone. So generally, in material having higher thermal conductivity, there are different type of zone. That is the first region that is very close to the fusion boundary, that is called your coarse grain heat affected zone. And the region just away from that one, that is called fine grain heat affected zone. And the region that at the interface of your weld metal, at the interface of your base metal and your heat affected zone, that is called your intercritical heat affected zone. Now we come to the first one, that is about your coarse grain heat affected zone, the region of the base metal just near to the interface that experience the maximum temperature, and due to that maximum temperature that is about more than the upper critical temperature of that material, so due to that we get the complete dissolution of the precipitate. Why it is called coarse grain? Because the precipitate at the grain boundary they are present, they provide the pinning effect to the grain boundary. Due to the dissolution of that precipitate, grain boundary becomes free, and once your grain boundary becomes free, it will grow in all the directions, and due to that we get the formation of the coarse grain. And one more thing, due to the dissolution of that precipitate, we get higher amount of the carbon and the nitrogen in the solution matrix that increases the strength and hardness of that region. So that's why if we talk about the region of your coarse grain heat affected zone that offer poor impact toughness and maximum hardness and strength as compared to other region. Now come to your fine grain region. Here, if we talk about that fine grain region that experience the temperature in lower than that one, and generally due to that low temperature, we get the partial dissolution of the precipitate, and we get some amount of the peeling effect to that grain boundary, and the formation of the fine grain in the region of your FGS period. If we talk about that intercritical, in that we get almost negligible dissolution of the precipitate, but we get some partial transformation of the austenite. To that we get the complex structure in the region of your intercritical heat affected zone. So means we get a continuous change in the microstructure along the region of your heat affected zone, and that is related with the property. Ultimately, we can say we get the variation, or we can get the mechanical property along the welded joint. So that's why it is very difficult to make that, means get the homogeneous structure in the region of your heat affected zone and in the region of your weld metal. Again, we are going to join two different materials. So this is for one side, on both the sides formation of the wide range of the heat affected zone, then ultimately we get a large amount of the heterogeneity in mechanical property for the region of weld metal, and that creates a problem. And during the condition, what happens? The softest of the region having poor hardness, we get a crack initiation from that region, and ultimately the final fracture of that region. So that is the problem. First thing related with the heterogeneity of the joint that we get in the region of your weld metal. This is for different region. This is an example for similar joining of the P92 steel with the P22 steel, and there is complete formation of that coarse grain, fine grain, and intercritical heat affected zone on both the side of a steel, means on P91 side and the P22 side, and due to that heterogeneity, we get different mechanical property at each point. This is about the similar one. Can we take a break of 5 minutes? Can take a break? Dr. Indu?
Yes, sir.
Dr. Indu?
Sir, Ranjit here.
Leonek? Jerome?
Yes, sir.
Ganesh? Are you here? Okay, can you take a break of
Sure,
5
sir.
minutes?
Sure.
Okay. I can just after the lectures, so I need a tea break.
Sure, sir. Sure.
So we will start, we will continue just after 5 minutes, okay?
Oh, okay, sir. Okay.
Dr. Ganesh? Yeah, thank you. Should I start?
Yes, sir.
Oh. Now, as I discussed, the major problem associated with that welding dissimilar joining TIG welding process in multi-pass, that is the wide range of that heat affected zone that create the heterogeneity in overall weldments. So now how we can minimize that problem? So there are two and three things that we can use. First one, we can change the process like from that multi-pass stick welding process, so we can use autogeneous laser beam welding, autogeneous TIG welding, or we can use electron beam welding process or activated TIG welding process. In all these cases, we will get small or narrow region of the heat affected zone. But the problem is that all these process we can use to join a plate of thickness up to 10 mm. It is not possible to get penetration more than that. So here some research work has been published related with that activated TIG process for the dissimilar joining, that is more convenient way to get a joint of plate thickness up to 10 mm for different type of the material. So here what parameter we consider in activated TIG, the main important parameter that is about your welding current voltage and other things. But the next thing that we consider in activated TIG process, that is about the application of the flux. Generally we use different type of the flux layer over the surface of your workpiece, and due to that the enhance the penetration in that process. So first thing, after optimizing that parameter, welding parameter, the second thing that we consider optimization of the flux for that penetration, and we use different type of the flux here for the dissimilar joining. P92 and P92 steel for different type of the flux. These are the weld bead profile. Here, without any flux, we get incomplete penetration, and by using CuO, we get the increase in penetration. In case of titanium oxide, silicon oxide, and other one, to the full penetration that we get in case of your titanium oxide, Cr2O3, and molybdenum oxide. But generally, the other parameter that we consider about the bead profile, that is about depth to width ratio. Now, up to if we consider that depth to width ratio to that optimum one that we get for the molybdenum oxide, so this is not fixed for one type of the material. I mean, if you are going to vary the material, you will get the different composition of that flux that will provide the optimum weld bead profile. Now the second thing, for activated TIG process, as I discussed, in case of your multi-part TIG, we get a wide range of the heat affected zone, and we get the variation in microstructure and mechanical property along that region. But if we come to that for activated TIG, the overall width of that heat affected zone that will be less as compared to your multi-pass welding process. Similarly, in case of your laser beam and in case of your electron beam welding process, due to the high power density, we get a narrow region of the heat affected zone as compared to multi-pass TIG. So due to that, we can minimize the overall heterogeneity across the joint. But problem is that again we get the different region, means the region just near to that interface, that is your quartz grain, that will offer that will show the different microstructure and mechanical property. After that, the last region of the heat affected zone, that is the intercritical heat affected zone, that will show the different mechanical property as compared to other one. So this is about the variation in the mechanical property along the weldment, and how that autogeneous welding process like activated TIG, laser, and electron beam welding process are helpful to enhance the mechanical property or to variation along the welded joint. Now I come to that friction stir welding process, that is friction stir welding, that is very common in case of your aerospace application, because in that case aerospace application we don't prefer the additional material, means we want to put the weight in the lighter one, so that's why we don't prefer the filler metal, because if we add the filler metal, to ultimately we get an increase in the weight of that overall welded structure. So that's why we prefer that friction stir welding. But in case of your friction stir welding, again, during the dissimilar joining, you will get the formation of unmixed zone due to the improper mixing of the two materials. So, but some papers are published, research papers or research were published related to the dissimilar joining of that different grade material. Especially if you talk about that aluminum and other one means low melting temperature material, it is easy to make a joint by using that friction stir welding. But if you talk about that steel material and other nickel based alloy, it is not easy to get a proper weld joint, but still some papers published related with that friction stir welding of that dissimilar steel plate up to 3 to 4 mm. But ultimately, if you talk about the in terms of application point of view, they are not useful, because in that case, first thing, it is not we are not going to use a plate of thickness 10 mm in service condition, and second thing, in case of the friction stir, we get a very narrow heat affected zone like your activated and other one. But the second problem related with that dissimilar welding by using friction stir process, that is the improper mixing of both the base metals. So that again create the problem during the service condition. Now come to the next point, means after making the joint up to it is okay, we can prepare the joint by using friction stir, activated TIG and multi-pass, and up to 8 mm, the most preferable one, that is activated TIG, laser and electron beam. And if the thickness is more than that, we prefer that multi-pass TIG welding process, but we don't prefer that friction stir welding for the joining of that dissimilar steel material. Now, after getting the joint by using multi-part welding process in activated TIG, that is okay. But in case of your multi-part TIG, as I discussed, if the weld metal solidify in austenitic mode, structure of the weld metal is austenitic, that will not create the problem. But if the weld metal microstructure, that is the martensitic, and there is a fresh martensitic formation, so that will create the problem. Ultimately, to improve the quality, to improve the mechanical property of that joint, we perform the post-weld heat treatment. So ultimately, that is with the tempering of martensite that is available in the region of your heat affected zone, coarse grain heat affected zone, and in the region of your weld metal. So that is okay, we can perform that one, but this is a time consuming process. Also the cost will take some high cost for that one. So that's why we don't prefer the post weld heat treatment in all the cases. If it is very urgent, in that case we perform. But again, that is associated with some type of the problem, means during the process of the after getting that dissimilar joint, if you are going for that post weld heat treatment, so at higher temperature, generally we perform it in the temperature range of your 700 to 780 degrees Celsius, depends upon the application, because there are different stage of tempering. So generally we perform the last stage of tempering, in which we get the formation of the oxides and carbon, not oxide, carbides during the process of the heat treatment. But due to the diffusion of that carbon from that one side to second side, again that will create the heterogeneity. Means during the process of the post-weld heat treatment, carbon diffuse from higher side to lower side. In that case, what happens when carbon diffuse from one to other side, in the region of your build metal, if there is a presence of chromium and other carbide forming element, so that get combines with that carbon and lead the formation of the chromium carbide. So means in a very narrow region, that is in about microns, we get the two region. One is your carbon depleted due to the movement of carbon, and second one, that is your carbon enriched zone due to the movement of carbon from one to second side, and that form the chromium carbide in that region. So that is called your enriched zone and carbon depleted. Sometimes also refer soft zone and hard zone. So again, that will create the heterogeneity in very narrow region, and always for that diffusion for all type of the joint, means for activated TIG joint, for multi-part TIG joint, or any type of the joint here, due to the diffusion, that black that is image captured in optical micrograph, that black region that is called your carbon enriched zone, and that offered the higher hardness, and here the light region that is your carbon depleted zone, that formed due to the diffusion of the carbon from that region. So here you will get the lower amount of the hardness. This is about the hardness graph of that region. In the bright one, we get the maximum hardness, and in the lower region, means your carbon depleted region, we get the poor amount of the hardness. So again, during the service condition, due to the formation of carbon depleted zone, we get the crack initiation from that region. So again, that is the problem associated with the dissimilar joining if you are going for the post-weld heat treatment process. This is the organic electron microscopic image that dark field, and this one about your light field. It is very clear there are small number of chromium carbide particles that are available in large density in that region. Here is the free region that is very clear due to the moment of diffusion of their carbon. Now, that hardness, that the width of then that soft and hard zone, that again depends on the time and temperature. Means post-weld heat treatment time and post-weld heat treatment temperature that affect the overall size of the soft zone and hard zone. So generally, if we increase the size, if we increase the temperature from suppose 600 to 700 or 762, in that case we get the increase in size of that one. And again, if you are going to increase the time of that one, generally we prefer the post-weld heat treatment time for 1 to 2 hours, but still we are going to increase that one, we get an increase in size of that soft zone and hard zone, and it gets stabilized after a certain period of the time, depends upon the material. Means for different material, that stabilizing temperature for their soft zone and hard zone, that is different. To here the image that shows the effect of that different post-weld heat treatment time. First one that is about your 1 hour, second one about 2 hour, and third one is about your 10 hour, and it gets stabilized after 10 hour of the time. And here we get the increase in size of that soft zone with increase in the duration of that one, and ultimately we get the effect of the soft zone on the hardness value. To means there is a formation of that micro region having different hardness and strength that will create the problem during the service condition. If you talk about the region of that hard zone, the different type of the carbide formation take place in that region due to the movement of the carbon that get combined either with chromium or molybdenum that present in that region and form the different type of the precipitate in very narrow region. Now, if you talk about the post-weld heat treatment effect on the region of your heat affected zone, so generally just after welding in heat affected zone, we get a continuous change in the microstructure and mechanical property as we move from the interface. Suppose this one is weld interface, as we move from the interface to the base region through that heat affected zone. Now, but after post-weld heat treatment, we get stabilized microstructure in the region of your heat affected zone. Means ultimately we can minimize the heterogeneity across the region of your heat affected zone by that post-weld heat treatment. So means once one side we are getting the benefit of that one, but at second side, but a second side, due to that movement of that diffusion of that carbon, we get the formation of carbon depleted and carbon in zone. So that will create the problem. So once one side you are getting the benefit of that one, and then one side you are getting the loss of the heterogeneity due to that diffusion of that carbon element. Now, this is about the EPMA study of that one that show the diffusion of the element and formation of that carbon enriched and carbon deflected zone. In case of your carbon enriched, we get the higher amount of the carbon percentage in that region and lower amount of the iron. Now, by using a TEM image, we can characterize the formation of that precipitate, what type of the precipitate are formed in that region. And as I discussed, the main precipitate that form in that region that are chromium enriched carbide and molybdenum enriched carbide. Now, if we talk about the effect of that heterogeneity on the mechanical property. So in that case, I discussed there are dissimilar plate. So in that case, we get the heterogeneity throughout the weldment. Means in your heterogeneity, how will you measure the heterogeneity? So in that case, we use different parameters and we perform different type of the mechanical test. The most common one that we use, that is the hardness variation. By making that hardness variation, we can clearly get the heterogeneity along the weldment. So first thing that show for this welded condition, in that case, the maximum hardness that we get in the region of your weld metal. After that, if we move toward the region of your heat effective zone, we get the increase in hardness. After that, we get reduction in the region of your jet, and the minimum one that we measure in the region of your intercritical. And after that, there is a formation of that base metal. Now, this is about variation in that also related with the variation in the microstructure along the region of your that weld metal. Similarly, if we come to the second region, that is about the region of P22 steel, again the reduction in FDH, and after that minimum one in the region of intercritical heat exchange zone. Overall, throughout the weld, we get the variation in the chemical property, and after performing a post-weld heat treatment, we can minimize the difference of the maximum and minimum hardness in the region of your HZ, but at the same time, due to the formation of the carbon in the zone, we get the maximum or peak hardness in that point. So that again create the problem. If you talk about the test that we perform, that is related with the tensile testing. So generally, in case of your tensile test, what we do, just after deposition, we prepare as per STM standard. So in that case, we prepare two type of the specimen. One is about your transverse specimen that cover the region of your weld metal, heat effective zone, and base metal. One we prepare the longitudinal. This is all about the weld metal. So the most commonly we prepare that transverse specimen, and how we check the quality of that weld. If the failure occurs in the region of your base metal, means we have two different base metal in this similar joint, and one obviously one have higher strength and lower. So if the failure occurs from the weak region of the base metal, then your weld joint is safe for the application point of view. But if it fails from the region of your weld metal, so that will not offer intended function during the service condition. So that's why we check the second thing, that is about the tensile property of that weld joint. And for different type of the things, if we talk about the friction stir welding, as we discussed, due to the improper mixing in the region of your weld metal, we get the failure from the region of your weld metal during the service condition. We get the failure, not service, during the edge welded condition. If we perform the tensile test, we get the failure from the region of your weld metal, and we get the tensile strength lower than the strength of the base metal. So in that case, we don't prefer that type of the joint. That is the problem related with the friction stir welding if you are going to use for the steel plate and steel material. Now, come to your service condition. This is steam heater section. This is the made of your 91 material, and there are so many steam tubes that is made of your P22 steel. And here there is the dissimilar joining at that point. Now, after that is exposed at temperature of 570 degrees Celsius for that period of time, 79,000 of hour. So in that period of the time, as I discussed, we put that weld joint in service condition just after post-weld heat treatment. So just after post-weld heat treatment, we get a narrow region of your soft zone and hard zone. And generally, we get the increase in the size of the soft and hard zone. This is the region of your soft and hard zone after that much period of the service. So generally, after again, if you are going to use that one, we get the failure from the region of that point during the service condition. So that's why we should take care of the formation of your soft zone and hard zone during the service condition, and how we can minimize that things. If we categorize that region, means hard zone and your soft zone, so again we get the formation of so many precipitate in the region of your hard zone and the carbon deflected region in that soft zone. So that is about the microwave. Now, if you talk about the service condition, that is about your long-term service condition. There are two types of the service we perform. where material is subjected to high temperature. So in that case, the thermal stress will be something. After that, during the cooling, that is subjected to the room temperature. At that point, overall the thermal stress that will be different. So that thermal stress comes due to the application of that one, that is related with the creep rupture strength, and other one also. So during the creep condition, during the high temperature and loading condition of that welded joint, we get the failure either from the weak region of your heat affected zone. I discussed three different regions: coarse grain, fine grain, and intercritical. So either due to the heterogeneity in the mechanical property along the weldment, we get the failure from the region of your intercritical heat affected zone. Suppose this one is your weld joint, and this one is the region of your heat affected zone. Here, this is the CGHZ, this is the ICHZ. Here you will get the ICHZ. So we get the failure either from the region of that intercritical heat affected zone, or here due to the post weld heat treatment. Here you will get the formation not in CGHZ, just near the interface we get the formation of that soft region. So either we get the failure from crack initiation or failure from the region of soft zone. Here this is the published work. In that we get the failure in the region of your soft zone that formed just after the post weld heat treatment, and we get the failure after a 10,000 hour of the service period. So that is about the major failure that we get in case of your dissimilar joint. If you talk about especially about chromium molybdenum steel dissimilar joint. Now, how the formation of that soft zone and hard zone take place during the service condition and your placement condition. Suppose this one is your martensite and one side there is benite. Here there is a presence of the carbon element, a small carbon element. So during the process of the heat treatment, we get the diffusion of that carbon element from here to here along the boundary. And due to the diffusion of the carbon, here we get a formation of the soft zone. They are deflected from the carbon, and that region that is called pro-eutectide ferrite region. And when carbon diffuse from that point and comes along that boundary, here there is a presence of the chromium, and it get combined with the chromium and form a layer of chromium carbide in very narrow region. So in the narrow region, in about microns, we get the formation of both soft zone and hard zone. That hard zone, that is okay, that will not create the problem, but that the carbon deflected soft zone that facilitate the crack initiation during the process of the service. So that is the problem during the dissimilar joining and their service condition. So how we can minimize that type of the problem, especially if you talk about the 22 and 91 steel. So in some research that has been proposed about the application of that nickel based filler, because why we are going for that nickel based filler. So generally that nickel based filler, they solidify in austenitic mode, and the end structure of that weld metal, that will be the austenite. So if the end structure will be the austenite, so that don't require any type of the post weld heat treatment. Generally we need post weld heat treatment in case of your martensitic steel. If we talk about that austenitic steel, we don't require any type of the heat treatment. So that's why we can use nickel based filler, and most commonly that we use 82 and 617 in conal filler to make a joint of that 22 and 91 steel. We can also use some interlayer to stop the diffusion of the carbon element from that one side to other side, or from base metal to weld metal. And by stopping the diffusion of that carbon element during the process of the post weld heat treatment, we can improve the overall performance of that dissimilar weld joint. Now, again one problem that we face in case of your nickel based filler, we don't require any type of the heat treatment, that is okay. But in case of your nickel based filler, that is not matching with P22 and P91 steel. So in that case, we get the formation of your unmixed zone, that is peninsula and island in the region of the weld metal just near to the interface. So at room temperature service condition, that will not affect the mechanical property of the weld metal. But again, during the service condition, that may create the problem. So, but still research is going on for that topic. It means how it will affect the overall performance, means the formation of that unmixed zone that promoted by nickel based filler, how it will create the problem during the service condition, and how it will affect the overall mechanical property, because we will not get any effect at room temperature, but service condition research that is going on. So how it will affect, we don't know any idea about that one. This image show the variation of the element across the interface, and due to that variation, we get the formation of their soft and hard zone at that point. And we get the major variation, especially about your chromium, iron, and nickel element across the interface. Now, the second topic related with the dissimilar welding, that is about the diffusible hydrogen content. Till now, if you are interested to ask any question, you can ask anyone. Dr. Ganesh, Nalgaya, Usha.
Yes, sir.
I know my topic is more related with that welding and other things. I don't know how much you are able to understand the things that is especially related with the research and other things. But still, if you are interested in research work and other, you can ask the question, and I'm also open to work with you if anyone interested, because all the things are related to metallurgy and welding things. The topic related to design I covered in first half, but not much as your point of view. So still, if you have any doubt regarding the things, you can ask anyone.
Yes, participants, if you have any query, please ask. I think, sir, participants have no query. So please
Okay,
continue.
so I can proceed. Yes.
Yes.
Now the next topic related with the dissimilar joining and the major problem, that is about the hydrogen content. Actually, during the process of the joining as discussed, there are three things. One is about after discussing their geometry, welding parameter, and other things. If we come about the joining, so there are three things that we consider. First one about the microstructure in the region of your weld metal. After that, hydrogen content, and third one about the residual stress. Now, material and microstructure, we cannot control the material and microstructure because that is related with the metal. So we cannot, means for a specific application, we cannot change the material, we can upgrade the material. So means first thing, the always constant means if you talk about the material and microstructure, if there is a crack susceptible microstructure like Martin said, we can't do anything in that case. We can perform the post-weld heat treatment to temper that one. So, but we cannot change the material. So first thing that is okay. Now, if you talk about that hydrogen content, how it will create the problem? Actually, hydrogen content we get from two sources. One either from the environment, and second thing, if you are going to use shielded metal arc welding or submerged arc welding to join a dissimilar plate, so in that case, the covering that we use for that one, there is moisture content, and if this moisture content comes in the region of your weld metal, so there are two type of the hydrogen comes. One is called your trapped hydrogen, and one is called your diffusible hydrogen. Trapped hydrogen once get trapped in the region of weld metal, that will not create the problem. It remain at one position. Now, if you talk about the diffusible hydrogen, if diffusible hydrogen get trapped in the region of your weld metal, it will move from one region to second region, depends upon the temperature and service condition. And when it move from one location to other location, it will create the cavity inside the region of your weld metal. So once a cavity is created, again that is the we can consider like a stress concentration. So once a stress concentration point created inside the region of your weldment, so we can create the crack initiation from that point, and ultimately we can get the failure from that point. So that's why diffusible hydrogen content measurement of that one, and how we can minimize that one is very necessary in case of your dissimilar joining. Now the crack failure associated with the diffusible hydrogen, that is called your hydrogen induced cracking. The third important parameter that your residual stress. Now, residual stresses that come due to two things, either due to the application of the high heat input, and second thing due to the transformation, metallurgical transformation means, suppose your base metal have austenite, and after heating, it will transform from austenite to cooling that in your martensite. So if there is going to change the microstructure from that austenite to martensite, austenite that have FCC structure, and the martensite had body center tetragonal. So if we are going to change from FCC to BCT, we get the lattice distortion of the structure. Due to that lattice distortion, that is called your bend distortion, we get some amount of the strain in that region, and due to that strain we get some amount of the residual stress. The second source of the residual stress, due to the variation in thermal expansion coefficient of these two metals, we get some amount of the residual stress in the region of your weld metal and in the region of your heat affected zone. So now come to your first point, hydrogen content, how we can control the hydrogen content and how we measure. So generally there are various methods are proposed to measure the diffusible hydrogen content in the weld metal. Now it is not easy to measure the diffusible hydrogen content in multi-pass welding, but for a fixed parameter, means once we optimize the welding process parameter, for that optimized welding process parameter, we can measure the amount of diffusible hydrogen at a fixed level. So generally what we do, we deposit a layer over the surface of your workpiece and cut that layer, and we put it into the glycerin or mercury solution, and due to the displacement of that glycerin or mercury solution, we measure the amount of diffusible hydrogen. So the most commonly one that we use, that is your mercury method. So in your mercury method, what we do, we prepare a sample like this. There is the sample size. There are 3 pieces, 1, 2, and 3. So that is piece that is called your runoff piece, and that is called your runoff piece, and that is the center one that we utilize to measure the diffusible hydrogen content. Now after making that 3 piece, what we do, we fix it in that copper fixture. This is the copper fixture, and we fix that 3 piece, and after that we deposit a layer over the surface of the workpiece. Means what we do, we deposit a layer for that optimized welding process parameter, and once after deposition, what we do, we remove that run on and run off piece, because we require only the center piece. And after getting that center piece, what we do, we merge that center piece into the liquid nitrogen at temperature about minus 70 degrees Celsius or 78. Here we capture the diffusible hydrogen present in the region of that center piece. And after capturing that diffusible hydrogen, because at that temperature it is not easy to diffuse the hydrogen from one place to other place. So after capturing that hydrogen at a low temperature, we allow it to, we put it into the mercury solution. This is the mercury or glycerin solution, depends upon which process we are going to use. And here we put that sample, means center piece we put here in that part, and due to that at the room temperature, when the sample comes at room temperature, so that diffusible hydrogen comes from that sample and provide the displacement to mercury. So here we measure the displacement, and with the help of that displacement or difference, by using that formula, we can measure the diffusible hydrogen content. This is just after deposition, and after deposition, what we do, we remove the run-on and run-off piece, and we get the center piece that we place in the mercury solution. And after that, with the help of that displacement, we calculate the diffusible hydrogen content. So once if the diffusible hydrogen content is a major criteria for the joint, so we can also optimize the parameter on the basis of diffusible hydrogen content. Generally, the main aim of that, the major thing that we use to optimize the parameter, for that we consider the weld bead geometry, especially about your depth of penetration and bead width. But if the diffusible hydrogen content or hydrogen induced cracking like thing, that is the major criteria. So in that case, what we do, for different parameter, we perform that diffusible hydrogen content measurement, and the parameter that to provide the minimum diffusible hydrogen content, we consider that one as the optimum one for that next process, or you can say for the multi-pass welding process. Now come to that next part, that is about the residual stress, how it will create. One more thing, if the diffusible hydrogen content in less amount, we know that will not create the problem. But what happens if your diffusible hydrogen content gets combined with the crack susceptible microstructure? So in that case, that may lead the catastrophic failure. Means it is not required that diffusible hydrogen content should be in high amount. A small amount of the diffusible hydrogen content may also create the problem if it get combined with the residual stress or your crack susceptible microstructure. Now, if we talk about the residual stresses, that is our locked in stresses present in any type of the engineering component, even when there is no any external load, and they develop primarily due to the non-uniform volumetric change in metallic components. irrespective of that manufacturing process such as heat treatment, machining, mechanical deformation, casting, welding means for any type of the manufacturing process we can get that locked in stresses or residual stresses. Now the maximum value of the residual stress doesn't exceed the plastic limit of the metal, because in that case if the residual stress comes in the region of your weld metal or any manufactured product exceed the plastic limit of the material, to in that case it will create the failure and it will lead the failure of that component. So residual stress, if we talk about the nature of that one, it may be tensile or compressive. Especially if you talk about that welding process, the residual stress in welded joint primarily develop due to two things. First one about the differential weld thermal cycle, means heating peak temperature and then cooling up to the room temperature. So means your weld region experience a variety of the cycle, number of cycles related with high temperature to your lower temperature. After that, the second thing that is related with the residual stress, that is about the change in microstructure, especially if there is change from the austenite to your martensite. So now type and magnitude of the residual stress vary continuously during different stage of the welding, means in your heating state the magnitude will be different, in your cooling state the magnitude will be different, because in heating stage your metal will be in molten state, so in that case the magnitude of that one will be different. And after cooling just from high temperature to room temperature, that will be in the solid state, so in that stage the magnitude of the residual stress will be different. If we talk about the welding, how we can control their residual stress, means we cannot completely we cannot remove the residual stresses in the weld metal, but we can minimize the region magnitude of the residual stress by optimizing the weld groove geometry. Means the residual stress that depends upon the amount of the filler metal deposited, or we can say amount of filler metal that is related with the heat input. So overall residual stress magnitude depends upon the overall heat input. So by minimizing that overall heat input, we can minimize or we can control the amount of the residual stress. So generally, suppose I want to join two plates of different groove geometry. One that is about groove geometry here, that is about your 70-degree, and second one, suppose this one is your narrow one, that is about your 40-degree or 45. So in second case you will get less amount of the metal deposition, so in that case the overall heat input will be less and overall magnitude of the residual stress will be less. So by optimizing the groove geometry, now we can ask in one case there is 70-degree in 45, in second one 45-degree, so we need less amount of the filler metal, ultimately cost required will be also less and the overall residual stress and distortion will also be less. So why we are not going for why we are not using that 45-degree, why we are going for optimization? Actually thing is that if you are going for narrow groove, the major problem associated with that, the application of the filler metal. So in case of very narrow groove design, it is not easy to penetrate in the region of narrow region of that root one. So that's why we optimize that groove geometry. In that case we can get the proper reaching of that filler metal to that point, means at the root point. So generally by optimizing that one, generally direct we cannot minimize the groove opening groove angle. We have to optimize that groove geometry, and after optimization we can use to minimize the heat input and the residual stress for that process. So one thing, the residual stress that comes due to the heat input and due to the application of the filler metal, we can minimize by using that one, by optimizing the groove geometry. Now the second thing, the residual stress that comes due to the formation of the austenite to martensite. As I discussed, the austenite that has FCC structure. In FCC crystal structure, if you know about the crystal lattice, that parameter, lattice parameter A, B and C, that will be equal, and that alpha, beta, gamma, that will also be equal. But in case of austenite to martensite, if there is a formation of that body central to trigonal, here A is equal to B but not equal to C. In that case, we get the distortion in one side. So due to that distortion, that is called your bend distortion, as I said, due to that distortion we get some amount of the strain in the region of your weld metal. So due to that strain, the residual stresses comes in the picture, and that we cannot remove by optimizing the groove geometry. To remove that type of the stress, we perform the post-weld heat treatment just after the welding. So that is about the residual stress. Here show the about the Martin-City transformation, and due to that we get the increase in the volume, because if A, B, C that is equal, volume will be different. If A is equal to B but not equal to C, means there is increase in the size of that C. So we get the increase in volume of that one. So due to that increase in volume, we get the higher amount of that one residual stresses. Generally, if you talk about the residual stresses variation, in case, as I said, in case of your narrow groove design, we get less amount of the residual stress because of the less amount of the filler and heat input. The other two geometry that we can also use to minimize the residual stresses, here for the different type of the groove geometry that have been presented to detect the residual stress in the region of the weld metal. First one, that is your equal double V groove geometry, and second one is your unequal V groove geometry. So in that case, again, we can control the amount of the residual stress by using different type of the groove geometry. And second thing, how we can measure that residual stress, especially if we talk about that welding process. So there are so many methods like your deep hole drilling, blind hole drilling, after that X-ray diffraction, neutron diffraction. So, but in case of your welding process, the most commonly that we use, that is your blind hole drilling and deep hole drilling. If you want to measure the residual stress at the upper surface of the metal, in that case we use blind hole drilling technique. But if you want to measure the residual stress throughout the thickness of the plate, in that case we use that deep hole drilling technique to measure that one. Here that image show the variation in the residual stress along the thickness of the plate. Here the plate thickness is more than 15 mm. So as I said, in case of plate thickness more than 50 mm, we use double V groove joint. And in case of your double V groove joint, again we can increase or decrease the cross section area from top and bottom region, and we can see the effect of that change in groove geometry in the overall residual stresses variation, longitudinal and transverse along the welded joint. Here that one show the variation along the weld joint, one that show along the variation along the thickness, and second one that show the variation along the in the transverse direction. In that we cover the region of your weld metal, heat affected zone, and in the region of your base metal. If you talk about the next one, that is about in dissimilar joint, that is your unmixed zone formation. So that occurs mainly due to the variation in composition of your filler metal and your base metal. So in that case, some portion of that base metal that get melted but unmixed with the weld metal and comes in the region of your weld metal. So that again create the heterogeneity. This is the region of your base metal that comes in the region of your weld metal. So if the region directly attached with the base metal, so then that is called your peninsula. And if it get terminated from that point, so then it is called your Iceland. So again, the major problem that is associated with that one, there is a formation of the unmixed zone. So how we can remove that unmixed zone formation in dissimilar joint? So that one by we can minimize by using autogeneous welding process, because in case of your autogeneous welding process, we are not going to use any filler metal. So in that case, we can avoid the problem related to the unmixed zone formation. So I'm going to stop up to here. There are so many lot of things, but I think up to here it is sufficient. Yeah, thank you. Now, if you have any query, if you want to ask anything, you can ask.
Participants are requested to ask queries. Any questions from participants? I think, sir, there is no question from the end, and we are very thankful to you, sir, Chandan sir,
Thank you, Dr. Indu.
for our
Thank you,
accepting
Rajesh
our
sir.
invitation, for being expert in this session. Your session was really very interesting, innovative, informative, and we seek your guidance and cooperation in future also, sir.
Oh, thank you.
Thank you very much, sir. And I request participants to join back at 2:15 p.m. There is break of half an hour, and we'll be meeting back at 2:15 p.m.
Okay.
Thank you.
Yeah, Ranjit sir, I will share the slide.
Yes, sir. Yes,
Yes,
sir.
sir.
Because there is,
Yes, sir. Participants are asking for slides
there
also.
is major change because that slide I shared that is completely different from that one.
Yeah, I've
And
seen,
after
sir.
that, I include the major portion of the design because in first one there was complete metallurgy portion.
Yes.
So I will share the new one. Okay.
Sure. Thank you, sir.
Sure, sir.
Yeah,
Then
thank
I
you,
will
sir.
share with the participants, sir.
Okay. Thank you, sir. I will share.
Thank you,
Thank you.
Chandan, sir.
Thank
Thank
you,
you
sir.
very much.
Thank you.
Have a nice day, sir.